Hello friends, in this lecture we will cover the next topic of our unit number 3, that is flip-flop. And in flip-flop we will cover the first two types of flip-flop, that is SR flip-flop and the D flip-flop. Now the learning outcomes. Now after studying these topics, students will be able to understand the working of the first type of flip-flop, that is SR flip-flop, and the working of the D flip-flop. Now, what is flip-flop? Now, flip-flop is a sequential circuit. As we know, the difference between the combinational circuit and the sequential circuit. If you think about the combinational circuit, then the output of our combinational circuit depends on the present input only, while for the sequential circuit, the output depends on the present input as well as the past output. That is the main difference between our combinational circuit and the sequential circuit. So the flip-flop is a memory element which is capable to storing 1 bit information. As in previous lecture we covered the 1 bit memory cell, and why flip-flop is called as an 1 bit memory cell, and one flip-flop can store only 1 bit at a time. That's why it is called as a memory element that is capable to storing 1 bit of information. And it is also called as a bistable multivibrator since it has two stable states, that is either 0 or 1. That's why the flip-flop is also called as an bistable multivibrator. Now this shows the block schematic of the flip-flop. Now left hand side there are a number of inputs are available, and on right hand side there are basically two outputs, that is Q and Q bar, where Q is the normal output and Q bar is the inverted output. Means Q bar is just inversion of our Q. Now, which are the different types of flip-flops? Now, flip-flops are basically divided into 4 types, out of which the first type of flip-flop is the SR flip-flop, and this flip-flop is also called as an set reset flip-flop. And why this flip-flop is called as a set reset flip-flop? This topic we will cover in the next topic. Then the second type of flip-flop is the D flip-flop or delay flip-flop. Then third type of flip-flop is the JK flip-flop, and the last type of flip-flop, that is T flip-flop. Now let's start with the first type of flip-flop, that is SR flip-flop. Now the SR flip-flop is the simplest type of the flip-flop, and it can be constructed by using your universal gates. Means you can design or you can construct your SR flip-flop by using your only NOR gates or by using only NAND gates. Now this symbol indicates total number of two inputs, that is S and R, and total number of two outputs, that is Q and Q bar, where Q is the normal output and Q bar is the inverted output. Now let's see the logic diagram of the SR flip-flop by using your NAND gate only. Now here total number of two NAND gates are used, NAND gate 1 and NAND gate 2. And one input to your NAND gate 1 is the R, and one input to the NAND gate 2 is S, and output of your NAND gate 1 is Q, and output of your NAND gate 2 is Q bar. Now here the output of your second NAND gate is connected with the first, means one input to your first NAND gate. Similarly, the output of your first NAND gate is connected with the one input to your second NAND gate. That's why this structure is also called as a cross coupled NAND gate. Cross coupled. Now why cross coupled? Because the output of your first NAND gate is connected with the input of the second NAND gate. Similarly, the output of your second NAND gate is connected with the one input to your first NAND gate. Now as total number of inputs are 2, so total number of input conditions are 4, that is when S equals to 0, R equals to 0. Similarly, when S equals to 0, R equals to 1. Similarly, S equals to 1, R equals to 0, and the last condition, that is S equals to 1 and R equals to 1. Now let's see the first case, that is when S equals to 0 and R equals to 0. Now this is our logic diagram by using your NAND gates. First of all, the input to your first NAND gate is the R and output from your second NAND gate, and similarly input to your second NAND gate is the output of your first NAND gate and one input, that is S. Now the case number 1 is S equals to 0 and R equals to 0. As we know, as per the truth table of our NAND gate, if any one input is 0, then output is forced to be equals to 1. So your Q equals to forced to be equals to 1. Similarly, your Q bar is forced to be equals to 1, and it doesn't depends on the second input. If any one input to the NAND gate is 0, then its output is forced to be 1. So the our conclusion for the first case, that is when S equals to 0, R equals to 0, the output do not change, means the flip-flop is in rest condition. Now what is rest condition? Now if you observe, the outputs of your first NAND gate and second NAND gate are the Q and Q bar, means your Q and Q bar should be complements of each other. Means if suppose Q equals to 0, at the same case your Q bar should be equals to 1. Similarly, if suppose your Q equals to 1, then at the same uh, state your Q bar should be equals to 0, means your Q and Q bar should be complements of each other. But for this case, means when your S equals to 0, R equals to 0, then output of your first NAND gate and second NAND gate is forced to be equals to 1, and that indicates your Q and Q bar are not complements of each other. That's why the output is not going to change. That's why your flip-flop is in rest condition. Similarly, the second case, that is when S equals to 0 and R equals to 1. Now again, when S equals to 0 and R equals to 1, then what will happen? As one input to your second NAND gate is 0, that is S equals to 0. So your Q bar is forced to be equals to 1, means output of your second NAND gate is forced to be equals to 1. Now why this output is forced to be equals to 1? Because one input to your second NAND gate is 0, and as per the truth table of our NAND gate, if any one input is 0, then output is forced to be equals to 1. As Q bar equals to 1, so the second input to your first NAND gate will be equals to 1, means both the inputs to your NAND gate 1 are 1, that's why your Q will be equals to 0. Because as per the truth table of our NAND gate, we know if both the inputs are 1, then your output equals to 0. Similarly, the second input to your second NAND gate is equals to 0. Again for 0 0, your output equals to 1, and this will be continuous to be, means your Q should be continuous to be equals to 0 and Q bar should be continuous to be equals to 1. So when S equals to 0 and R equals to 0, this makes your Q equals to 0 and Q bar equals to 1, and this condition is called as an reset condition. As we know, in previous lecture we covered the 1-bit memory cell, and the conclusion of our 1-bit memory cell is that when our Q equals to 0 and Q bar equals to 1, then our flip-flop is in reset condition. Now the third case, that is when S equals to 1 and R equals to 0. Again same schematic. Now please check all the conditions, that is when S equals to 1 and R equals to 0. Now when S equals to 1 and R equals to 0, then as R equals to 0, then obviously the output of your first NAND gate, that is Q, is forced to be equals to 1, because if one input to the NAND gate is 0, then output is forced to be equals to 1. And as we know, the output of your first NAND gate is connected to the input to your second NAND gate. That's why both the inputs to your second NAND gate are 1. That's why the output equals to 0. In this way, you for this case, means when your S equals to 1 and R equals to 0, your Q is continuous to be equals to 1 and Q bar is continuous to be equals to 0. Means this indicates that your flip-flop will be is in set condition. As we covered in a previous lecture, that is when our Q equals to 1 and Q bar equals to 0, then our flip-flop is continuous to be equals to in set condition. And the last case, that is when S equals to 1 and R equals to 1. Now when S equals to 1 and R equals to 1, it is difficult to find out the Q and Q bar, because for the previous two cases one input is 0, that's why it is easy to identify, because if input is 0, then output equals to 1. But for this case, as both the inputs are 1, so your Q and Q bar should be no change in no change condition. So when S equals to 1 and R equals to 1, this makes Q and Q bar try to become 1, which is not allowed. Why not allowed? Because our Q and Q bar should be complements of each other, and so this condition is prohibited. when S equals to 1 and R equals to 1. Now the next topic, that is clocked SR flip-flop. Now if you see the previous SR flip-flop, in previous SR flip-flop we doesn't apply any clock signal, but to trigger or to turn on your sequential, any sequential circuit, you will require the proper clock signal. So what is clock SR flip-flop? The SR flip-flop using the gates is not practically usable circuit because they transmit the inputs to the output without any control. Therefore, for the practical approach, the flip-flop uses the additional control input, that is the clock, which is added along with the R and S input. Now here the same circuit is used, but here one clock signal is used. Now if you observe the truth table, now truth table is almost same. Now when S equals to 0, R equals to 0, then your Q and Q bar are in no change condition. Similarly, when your S equals to 0 and R equals to 1, for this condition your Q equals to 0 and Q bar equals to 1, that indicates your flip-flop is in reset condition. Similarly, third condition, that is when S equals to 1 and R equals to 0, then your Q equals to 1 and Q bar equals to 0. This indicates your flip-flop is in set condition. And for the last condition, that is when S equals to 1 and R equals to 1, then your flip-flop is in rest condition, and we always avoid to use this condition, that is S equals to 1 and R equals to 1. So from this truth table, our conclusion is that for only two conditions, that is for 0 1 and 1 0, our flip-flop is in set and reset condition. So these are the two usable states, that is 0 1 and 1 0, because for 0 0 your Q and Q bar are remain same, that is they are in no change condition. Similarly, when your S equals to 1 and R equals to 1, then your flip-flop is in rest condition. That's why for practical use we always avoid to use that is 0 0 condition and 1 1 condition. Now the second type of flip-flop, that is clock D flip-flop. Now D flip-flop is the simple gated SR flip-flop with an inverter connected between the S and R input. Now symbolic representation, only one input, that is D, then the clock signal is applied, and two outputs, that is Q and Q bar. Now how to design your D flip-flop by using your SR flip-flop. Now first of all, before going to design your D flip-flop by using your SR flip-flop, our conclusion from the truth table of our SR flip-flop is that for the first condition, that is for 0 0, and for the last condition for 1 1, our flip-flop is in rest condition and no change condition. So only two usable conditions are there, that is 0 1 and 1 0. So while designing our D flip-flop by using your SR flip-flop, we will use the inverter, due to which the S and R always the complements of each other, means we get our set and reset outputs for 0 1 and 1 0 condition. That's why, means that indicates when our S and R inverted with each other or complements of each other, then we will get the output, that is set and reset. That's why when we will use the inverter, then S equals to 0, R equals to 0 and S equals to R equals to 1, these input conditions will never appear, and this will avoid the problems associated with the SR flip-flop, that is when S equals to 0, R equals to 0 and S equals to 1, R equals to 1, that is in rest condition, means the rest condition or the no change condition will be avoided. Now that is our objective, to design our D flip-flop by using your SR flip-flop. Now here if you see the schematic, it's same, but the one inverter is used in between S and R. Now as due to this inverter, your S and R are always complements of each other, and remaining circuitry is same as that of our SR flip-flop. Now let's check the two cases, that is when D equals to 0 and D equals to 1. Now here, as the input to your D flip-flop is only 1, that's why total input conditions are only 2 as per the equation, that is 2 raised to n, means when our D equals to 0 and D equals to 1. Now let's check first condition. Now here the same circuit is used, but in between your S and R one inverter is used. Now due to this inverter, your S and R are always complements of each other. So due to these complements, the first and the last case of our SR flip-flop is always avoided, that is 0 0 and 1 1. Now let's check first case, that is when D equals to 0. Now when D equals to 0, then your S equals to 0 and R equals to 1. Now why S equals to 0? Because your D is directly connected to the S, and uh, in between D and R one inverter is used. That's why the output of your inverter equals to 1. That's why R equals to 1. And here the clock is applied, which is equals to 1. Now clock equals to 1 means that indicates the positive edge triggered clock. That's why the clock equals to 1. Now what will be the output of the third NAND gate and what will be the output of fourth NAND gate? Now as the input to your third NAND gate is 0 1, that's why the output equals to 1. As per the truth table of our NAND gate, as we know, if any one input is 0, then output is forced to be equals to 1. That's why the output of your third NAND gate, which is equals to 1. Similarly, the input to your fourth NAND gate are 1 1. That's why the output equals to 0. Now the input to your first NAND gate number 1 is 1, and one input to your NAND gate number 2 is equals to 0. Now let's decide what will be the output. As the input to your second NAND gate is 0, that's why your Q bar is forced to be equals to 1. Why? Because as we know, if any one input to your NAND gate is equals to 0, then output is forced to be equals to 1. That's why for this case your Q bar is forced to be equals to 1. As Q bar equals to 1, that's why the second input to your first NAND gate or NAND gate number 1 will be equals to 1. So the both the inputs to your NAND gate NAND gate number 1 are 1. That's why your Q will be equals to 0. As Q equals to 0, so the second input to your NAND gate number 2 will be equals to 0, because the output of your NAND gate 1 is connected with the input to your NAND gate 2. Again, if you check all the conditions, then you will get your Q equals to 0 and Q bar equals to 1. And as we know, if Q equals to 0, then Q bar equals to 1, then our flip-flop is in reset condition. Means the conclusion is that when our D equals to 0, then our Q equals to 0 and Q bar equals to 1. This will reset our flip-flop. This indicates our flip-flop is in reset condition. Similarly, let's check the second condition, that is when D equals to 1. Again same circuit. Now when D equals to 1, then S equals to 1 and R equals to 0. R equals to 0 due to that inverter, and clock equals to 1. Now in this condition, the output of your fourth NAND gate will be equals to 1 and output of your first NAND gate will be equals to 0, because the input to your third NAND gate are 1 1. That's why the output equals to 0, and input to your fourth NAND gate, which is equals to 1 0, that's why the output equals to 1. Now as one input to your first NAND gate is 0, that's why the output, that is Q, is forced to be equals to 1. Now when Q equals to 1, then the second input to your NAND gate number 2 will be equals to 1. So both the inputs are 1, that's why the Q bar equals to 0. Now when Q bar equals to 0, so the second input to your first NAND gate will be equals to 0, and this will continues to your Q equals to 1 and Q bar equals to 0. And as we know, when Q equals to 1 and Q bar equals to 0, then our flip-flop will be is in set condition. Now this is the conclusion from our D flip-flop, that we have avoided that two conditions from your SR flip-flop, that is 0 0 and 1 1. Here we are getting only set and reset condition. And this is how to design our D flip-flop by using our SR flip-flop.